Mr. Lin, I don't want to do math.
Okay, let's not do math.
Mr.
Wait,
What?
yeah, we're not going to do math. We're going to do trig. That's trigonometry.
That's like math.
That's right, the moment you've all been waiting for, trigonometry. Let's get started. We are skipping all the way to section 15.1. So here we go. So let's start with the basics. We're going to start with angles and rotation and radian measure. So I can mathematically express the relationship between the unit circle and radian measure. So we'll get to that here in just a minute. But first, let's spark your learning. Hey, NASA! So if you've never seen this before, astronauts train in something like this. It spins you around really quick, and it actually simulates G-forces. So when you're launching into space on a rocket ship, then your body's going to experience a lot of G-forces, so you got to be able to deal with that. And so they use this thing. It spins around in a circle really, really fast, and it uses angular momentum to simulate all of that gravity. So as normal, what is a mathematical question you can ask about the situation? What information would you need to know to answer that? So, how fast are they going? The distance that they are actually traveling around. So these are all good questions to ask. And they can actually be solved with just a little bit of information. So they give you the length of the arm, that's this part right there. So like here, so they give us that length, and then they say that it does 450 revolutions per minute. So based on just that amount of information, you can figure out how fast they're traveling, how far they end up traveling. From that, you can figure out the G-forces that they experience, all using, I almost said atoms, all using rotation and radian measurements. And or what we're about to learn is the unit circle. So let's get into it. Get started with anytime you're learning anything new, and I don't know how much trig you've had already, but there needs to be a common set of vocabulary so that we can use similar language. So that's what we're kind of going over here. So analyze angles of rotation and identify coterminal angles. So first of all, what we're looking at down here is an example of a unit circle, kind of. So a unit circle is a circle with radius 1 that we can then use to talk about all of these different angles. And so that's going to be coming back over and over again. So whenever we say unit circle, that's what we're talking about, a circle with the radius of 1 unit. So now, obviously, we're going to be talking about angles of rotation. So angles of rotation, and you'll see that we always typically use theta. That's the Greek letter theta. So anytime we use a variable, just like how we use x for numbers, theta typically stands for an angle. You can, of course, use anything you want, but good scientific or mathematical nomenclature is we use theta. If you're going to draw it, just something like that for angles. So when we're talking about the unit circle and we're talking about angles, so we always assume that they start in standard position, and that is referring to this part right here. So notice how, hopefully you know that an angle is two rays or lines that intersect, and how much they intersect, or like what angle they come in, is what we're referring to as angle. So in standard position, we always just assume your first ray is right there along the x-axis. That's just where everything kind of starts. So it begins at the origin and goes out along the x-axis. That's the initial side. Okay, so initial side is referring to that first ray. So then there is the terminal side. and the terminal side is this part right here. So that is the thing that moved. So if we have our two rays, our first one is here along the x, and then it rotates up this way, and then here we have our terminal side. Again, my drawings are amazing, I know. So angle of rotation, theta. You can always just assume that we are starting in standard position. The first side is here along the x-axis. The terminal side is the one forming that's going to move. That's the varying thing. Again, the terminal side is also going to start at the origin, and it's going to come out at some angle theta in relation to the initial side. Okay, so it stinks like COVID in here. So the angles typically will always, well, by standard, rotate counterclockwise. So as you kind of see up here, it's going counterclockwise. That is for a positive angle. So when the terminal sides of two angles of different measurings coincide, they are called coterminal angles. So if you have two terminal angles and they end up being on the same spot, then they are coterminal angles. So what that means is, I told you our positive thetas go around counterclockwise. So hopefully you can imagine that a negative theta would then go clockwise. So I assume this is referring to the angles that you played with in geometry had measures between 0 and 180 degrees. And that's great. So every angle out there, since we are on a circle, can be expressed as an angle of less than 180 degrees. Okay, but Mr. Lin, look at this one. Angles with measures 214 and negative 146. So how does that gonna work? So I'm sure you can kind of see on the picture already. So your 240 degrees goes all the way around, and it is the same as our negative 146. So when we start doing some trig based on like what triangles do these make and some trig functions, we can use, or the trig functions of 214 and negative 146 are both going to be the same because they are referring to the same position. So this is what they were talking about, the coterminal angles. You've got two rays here. You've got one being formed from 214 degrees, then you've got another one being formed from negative 146, and they're the same thing. So the angles can always be expressed as an angle less than 180 degrees. You just need a negative sign to help you do it. So I'll let you take a look at this. Identify the initial side and the terminal side of each angle. Do, 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 do. So the initial side is going to be right here. Initial side is always right here. Terminal side is this guy right there. Come on. Oh no, yeah, we're not gonna let Mr. Lin do this. We would never want to let him do it right. All right, whatever. So how are the angles related? How are they different? The angles share the same terminal side and initial side, so they are coterminal angles. The rotation direction is different. One is positive, going counterclockwise. The other is negative, going clockwise. Did I get them all right? Good, I didn't get confused or anything. Are there other angles that would be coterminal with the angles shown? Explain how you know. Yes, any angle that shares the terminal side is coterminal. Sure, why not? Yes, the angles that and that would also be coterminal to these two angles. No, so the answer is yes, I'm pretty sure of that one. So I'm not even going to read the no's. So, and if you think about it, if we come back up here to this picture, every time you go around 360 degrees, you're going to hit another coterminal. So you could essentially have an angle with, I don't know, whatever 360 plus that is, and you're going to have this coterminal angle. So one could say that there's an infinite number of coterminal angles. And I'm not going to draw that graph for you because I don't want to. Hey, look, just what I was talking about. So we have our first angle right here. Let's zoom in. So our first angle is at 71 degrees, but if we go all the way around, 71 plus 360, we've got 431 degrees. So these refer to the same angle. So let's see here. What does the curved arrow tell you about the angle, its direction of rotation, and how it goes all the way around? Is it possible to identify other coterminal angles? Yes. Let's type yes. Draw a sketch for your answer, and again, I'm not going to do that. There are two additional ways that you can get those coterminal angles. So we've got some of the terminology out of the way. We're all kind of speaking the same language. So now let's talk about this thing called arc length. So there is a relation between arc length and radius. As you hopefully remember, our radius of any circle is from the center to the outside of the circle, a straight line from the center, the distance from the center to the outside of the circle. Now, arc length refers to, so if you have a length right there, so the arc length is the distance of this circle going all the way around. So one would assume that it would be related to the angle in some way, shape, or form. So that's kind of what we're looking at. So we've got a couple of circles here on the screen. So this is a circle with radius of 1 unit, radius of 2 units, radius of 3 units. And they all have the same angle here of 200 degrees. So in each one of these cases, we are referring to just this part of the circle. So it's just a chunk of the circle, if you will. So we can make some inferences, if you will. So what are the similarities and differences of ABC, DEF, and GHI? So when they're naming these things, so look, A, B, C, D, E, F. So that's how the naming part of it works. I just want to make sure that you understand kind of what they're talking about. G, H, I. And I'm sure, and you will see this again, angles are typically named the same way with 3 letters. But, so what are the similarities and differences between ABC, DEF, and GHI? Select all that apply. The arcs are definitely not congruent. Remember, congruent is same size, same shape. The arcs are intercepted by the same central angle. Okay, I'll say that's true. The arcs appear to be different lengths. Yeah, I think that's a fair statement. The arcs begin and end at different initial and terminal sides. That's false. Arcs are formed by negative rotation, not this time. So compare the lengths of ABC, DEF, and GHI without any calculations. So the lengths of the arcs increase as the radius increases. So again, we can look at that, and as the radius increases from here to here, this length would get bigger. I hope that kind of makes sense graphically or visually. So this circle is bigger than this circle, or this arc length is bigger than this arc length. So that kind of makes sense. What is the ratio of the number of degrees in the central angle in the diagram to the number of degrees in a full circle? What does that ratio represent? So we've got 200 degrees here. How many degrees are in a total circle? So hopefully you're thinking to yourself, there are 360 degrees in a full circle. So that ratio is, I believe it's 5/9. I didn't pull out the calculator. I guess I could do it real quick, but this represents a portion of the full circle. Did I get it right? Yay! 5/9. You can check me out with a calculator, or you can do it by hand. You can just simplify this fraction by hand. So this ratio is kind of important. This ratio could probably help us figure out the arc length. So if we have the ratio of degrees versus the full degrees of a circle, so what about if we use the radius to then figure out the arc length? So the length of an arc is the length of the portion of the entire circumference. So do you remember how to find the circumference of a circle? Yes, Mr. Lin, we totally do. So the circumference, or C, is equal to pi, 2 pi r, I'd remember it. Or pi times the diameter, whichever one you want. So here we've got our three different circles labeled out. 2 pi r when the circle is 1 radius. The circle has a radius of 2, and the circle has a radius of 3. Remember, there's 3 circles. Radius of 1, radius of 2, radius of 3. So then if we just multiply the total circumference by this ratio, all of a sudden we now have these 3 different values which represent the length of the arc length. So if we were to take a string and put it on this part right here, and then pull it up, pull it tight, that would be the length of the arc length. So where are we? So okay, yeah, explain how I know. We just kind of talked through that. So then find the ratio of arc length to the radius for ABC, DEF, and GHI. So like, excuse me. So the arc length is this thing right here over the radius. So we've got like, so we'll just do 1 or 2 of them. So we've got 10/9 pi over the radius of 1, which equals 10 pi over 9. Then we've got, I'll switch colors here. So then we've got 20 pi over 9 divided by 2. So we have our radius of 2, which then equals 10 pi over 9. And guess what this one's going to equal? When we do that ratio, it's probably still going to equal 10 pi over 9. So the ratios are equal. Ratio of the arc length to the radius for all 3 is 10 pi over 9. So the fact that that ratio is the same means that we could probably use it mathematically, right? In math in general, we're always looking for ways to be more precise. So when dealing with angles and rotation and things like that in mathematics, as well as in like super precise research, academia type stuff, we're not huge fans of degrees. So the degree is kind of an arbitrary number. Somebody just said, let's throw 360 degrees in a circle. So when you get into like upper level math, it gets kind of hard to use degrees because it's kind of like the English system, where if you transfer degrees into something else, there's 360 of them, and it gets a little weird after a while. So what mathematicians and scientists tend to use is a measure called a radian. So a radian is the type of measurement that we're going to be using in this math class. So it's kind of important to know, number one, where it comes from. So a radian is so if we're looking at a unit circle. So again, a unit circle is a circle with radius of 1. A single radian is the length of the surface, the arc length of 1. So let me say that again. I'm stumbling over my words. So a single radian is defined by the angle that you get right here when you have an arc length of 1 on the unit circle. So that's kind of how we defined it. That gives us the ability to use fractions and to get an even more precise way of talking about angles as opposed to the degrees that we're kind of sort of used to. So naturally, we're going to need to know how to flip between angles and degrees, right? So engineering still uses degrees, especially when you're building things like buildings, walls, where you don't need that micro precision. You can use degrees and it's fine. You don't necessarily need radians when you're doing something like that. But maybe when you're dealing with an electron microscope or something that's a little bit more precise, you might need radian measures for that. So 1 radian is the angle associated with 1 unit length of the arc length. So let's see what that kind of means. So again, we've got theta. That's just the typical variable that we always use for angles is theta. So, and we can think about this again in terms of ratios. So there are 360 degrees in a circle. And if we look at our unit circle here with radius of 1, what is our circumference? Our circumference is going to be, oh, come on, pen, is going to be 2 pi r. R in this case is 1, so it's going to be 2 pi. So we could say for every 360 degrees, there is 2 pi of radians. So radians typically does not have a unit associated with it, so usually it's just marked as 2 pi, or RAD maybe. No, it's usually just marked, the angle is like blank, whatever radians. So, but we could say that for every 360 degrees, we have 2 pi radians. So 360 over 2 pi is our conversion factor. So we can then simplify that as to 180 degrees over pi. So that's your conversion factor. So for those of you in chemistry, this is going to be really easy, right? If you have degrees, if you have something like, 10 degrees, how many radians is it? So you're just going to multiply, like we did at the beginning of the year with stoichiometry and stuff like that. There are 180 degrees in a single pi. It sounds weird, but whatever. In a single pi, and then this is going to be your answer. You're just going to take 10 divided by 180, and typically we leave the pi in there for precision. And so, whatever that answer would be, 10 divided by 180, 180. And again, typically this is left in a fraction. So you would have like pi over 18, which I totally should have known that because you just, whatever. So this is typically how radians are going to be done. And so you can do the opposite too. So again, we've got our conversion factor, 180 degrees over pi. Let's say we have radians of, I don't know. So let's say we have like 1/4 pi, and we want that in degrees. So there are how many degrees per 1 pi? There are 180 degrees over pi radians. So then again, we can just, finish that out. So our pi's cancel out. So then we have 180 over 4. Which is equal to 45 degrees. Make sense? Kind of, sort of. Well, here is a chart that can help you out. So just like what we talked about, multiply measure in degrees by pi radians over 180, or convert radians to degrees, 180 degrees over pi radians. So I strongly encourage all of you to remember it the way that I just showed it to you, of canceling units out, because that's going to be way more helpful to you in your future careers, almost no matter what you do. Whether you go into math, science, or, I've used it in like my day-to-day, which, whatever, occasionally. I'm also a math nerd, so whatever. So here's a couple examples. So degree measures, so if we have 15 times pi over 180 equals pi over 12 radians. 700 degrees, again, this all works the same way. Negatives work the same way as well. So we've got negative 315 degrees times pi over 180 equals a negative 7 over 4 pi. And we can go from radians to degrees as well. So if we start with pi over 3 radians, pi over 3 times 180 over pi equals 60 degrees. So, I don't know. I don't want to insult your intelligence by going over every single one of those, but here are some examples that you can work through. I'm sure we'll have some in our homework, but whatever. Why is a conversion factor with degrees in the denominator used when converting 15 degrees to radians? I would say, again, so that the degrees cancel out and you have radians left over. And if you remember that kind of stoichiometry type stuff, then you will be in good shape. What do you notice about the sign of the angle in the equivalent degree reading measured? The sign is the same and indicates the direction of rotation. So that direction doesn't change just because we're switching from degrees to radians. You're just changing units. It's similar from going to, inches to feet or inches to centimeters or something like that. Today, unless we solve a real-world problem involving arc length. All right, let's see what they got for us. So the equation theta equals s over r. So again, that's going to be the arc length over the radius. Describes the relationship among three variables: central angle, arc length, created by s, okay, blah, blah, blah. So we can rearrange that to give us an arc length formula. Real-world problems involving circular rotation about a center point may involve arc length. So we would call that angular velocity. And we can use that to figure out how fast round objects are moving at the surface. So think, I don't know, planets. So Jupiter has a radius of about that many kilometers at its equator. What is the angular velocity in radians per hour of a point on Jupiter's equator? how far around Jupiter's axis does the point travel in 1 hour? How does the distance compare with the distance of about that many kilometers, traveled by the point on Earth's equator in 1 day? I think we have a little hint here. A point on Jupiter's equator makes a full revolution once every 9.9 hours. Okay, so here we go. We know up here, I'm just going to write down S equals R theta, where S is our arc length, R is our radius. So our radius here equals 71,500 kilometers. And so we want to know how fast you're moving. Where is it? How far around Jupiter's axis does the point travel in 1 hour? So we can figure out a speed here, so we can get a distance over time, because we have a time for a full revolution. So let's figure out the distance that this point on the equator would travel in a full revolution, and then we can use that speed to figure out the rest of it. Or velocity, if you will. Well, I think it would be speed in this case. Anyway, so our radius, so our theta is going to be all the way around, so 360 degrees or 2 pi. They want it in radians, so we're going to stick with radians. So our S we want to solve for is equal to 71,500 times 2 pi radians. Again, you typically don't include the word radians. So, okay, we're just going to plug that into our calculator. $71,500 times 2. Again, we're going to leave the pi in the answer. 143,000 pi equals S. So then we also know that the point on the equator makes 1 full revolution every 9.9 hours. So how does, let's see here, how far around Jupiter's axis does the point travel in 1 hour? So they want it in hours, so we'll keep it in hours. That's totally cool. So we know that the point travels this, I should say kilometers, this many kilometers in 9.9 hours. So we're going to set up our ratio of 143,000 pi kilometers over 9.9 hours. That's our ratio, and we want to know how far around Jupiter's axis does the point travel in 1 hour. So we're going to multiply this whole thing by 1 hour, but it's not really going to change our math at all. So we're going to take 143,000 divided by 9.9. So is that number. So let's see if they want pi. Yeah, it looks like they do want pi in the answer. I don't know, we'll see. So I'm going to go ahead and write down that number. 1, 4, 4, 4. How many fours? 1, 2, 3, 4. 4 fours, look at that. 0.44 pi. Kilometers per hour. Or I guess the hour dropped off. All right, so that's how you would do that full problem. I'm sure they have some questions for us to answer. So let's see what they got for us. So how many radians does the point travel in half of the revolution? So if it goes all the way around is 2 pi, so this would be 1 pi. I wonder if that will work. Oh, it does, okay. So when typing, you can type pi, and that's the same thing as the symbol pi, FYI. So find the distance traveled. So this is what they did. They rounded a little bit differently than what we did, and they multiplied into the pi, whereas we left the pi there. So if we go back to our calculator and just take that number times pi, you'll see that we get the same number that they did. 45,000 something, 45,378. So what are the units of the arc length? So it would be kilometers because our radius was given in kilometers. And kilometers around Jupiter's axis in 1 hour. So there you go. And oh, they gave us, this is almost the same distance that a point travels around Earth's equator in 1 day. So because Jupiter is so much bigger, if you are standing on the surface of Jupiter, which doesn't make sense because it's a gas giant, but whatever, in 1 hour you travel the same distance through space as you do an entire day here on Earth, which is kind of crazy, right?